Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already done so, go ahead and subscribe to this channel. And as usual, I request you to like this video if you really happen to like it. In the last couple of videos, we looked at the definitions of residual block, recurrent blocks when it comes to units. In fact, in the last video, we looked at how to add attention or what attention is in the context of U-Net. So let's put all of that in action in this video. So the goal here is to obviously write Python code. Of course, we'll go through the one that I already have. And again, have a quick look at our residual blocks and recurrent blocks, and also how we can add attention to these units and see which one wins out when it comes to segmenting or the data set that we have been working with for the last few videos, which is our mitochondria data set. Okay, so again, here is a quick summary of what we discussed in the last couple of videos. So a regular convolutional block has of course, inputs going into the convolution block, and you may have one or more convolutional actual convolutional operations followed by activation, and you can also have batch normalization as part of this, right? So you have convolution plus ReLU, and then output. When it comes to a recurrent convolutional block, within each convolution, the operation repeats multiple times, and how many times that you define as a user. And the residual convolutional blocks are where you have a typical convolution block, but then the outputs are actually summed between the convolution block output and also the original input itself, meaning this part, when we are training it, we are actually training it for the residual part, hence the name residual convolutional block or residual convolutional neural networks. And when you combine these two, you get R2 convolutional units. And again, as the complexity increases, the computation also goes up. Okay, hopefully that results in better segmentation in our case. So let's look at updating this block, or typical unit convolutional block that we have, with a recurrent. In fact, in this example, in this video, we are going to look at residual convolution block. There are libraries out there which I'll probably talk about in the next video, where you can import R2 blocks and so on without doing any much coding yourself. But it really helps if you can code these blocks yourself, so you understand exactly what's going on. Okay, so let's look at residual convolution block, like replacing the U-Net with res convolutional block, and also adding attention like I'm showing you here in this graphic, to a regular U-Net and also to a residual U-Net. Okay, a unit with residual blocks. So our goal here is, again, to look at regular unit, residual attention unit, and attention residual unit. Okay, these are the three things that we're going to look at. Now, in case, again, you're wondering what attention is, if you haven't watched the previous video, a quick summary: an attention right there takes two inputs, one coming from the one block right below, and the one coming from this skip connection part. Okay, so because this is coming right below, we'll have to change the dimensions. Again, we'll look at that as part of the code, and then add them together, and then follows through the ReLU activation and so on. Okay, so it takes two inputs, like I mentioned. G is the gating signal, and X comes from this skip connection. Okay, so now let's jump to the code and get back to the results here. So in the code, I'll explain a few things, but then let's jump back to see how the results would look like without wasting much of your time. Okay, so let's jump to our Spider IDE. Okay, so here is our Spider IDE, and this part of the code is going to show you the model itself, like how we are building the model. And I'll switch to the next part of the code, like this part of the code, where we are going to import the model that we are going to build here, and then train the network on the data that we're going to import. Okay, but first let's start by looking at the model itself. And again, you can Google search, you'll find many things on GitHub where they show R2 units and regular units and everything. So what I did was, I wanted to do something from scratch, but exactly not waste a lot of time in doing everything from scratch. So I got some of the code from this repo, and then I should admit this probably doesn't look much like what I got over there, but you'll see some elements of that code, okay, because I heavily modified it to customize it for this tutorial. And here is a paper on attention U-Net, and here is a paper about recurrent residual U-Net if you would really like to learn more about these two. Okay, so now let's come down to understand a few things here. So up here, a few metrics and losses. And dice coefficient, hopefully you know that Jacquard coefficient is like intersection over union, so this can be very useful to print out while we are training. Same with dice coefficient, I would say. And here are the coefficients, and here are the losses. Okay, and again, just a quick note, for example, Jacquard loss, we just put a negative before our Jacquard coefficient, which is our intersection over union, because we want to minimize, right? I mean, loss means we are minimizing it, and actual IOU, we are trying to maximize it. So the negative sign ensures that we are actually minimizing the loss and not going the other way. That's all there is to explain there. Now let's build some blocks that we are going to use to build our U-Net. So here, this I believe is this is a convolutional block right there. So the way we define this is you have convolution, batch normalization, activation. Convolution, batch normalization, activation, and finally dropout if you want to enable dropout. That's it. I like that this person, wherever I got this original code, kind of separated this batch normalization as a parameter that you as a user would like to enable or not enable. So if batch normalization equals to true, that means after convolution, batch normalization happens, and then activation. Convolution, batch normalization, activation. Okay. And dropout, if you would like to add dropout, just go ahead and put dropout equals to 0.2 or whatever. But right now we are not doing any dropout. Okay, so this is my convolution block. Nothing new. You probably saw this many times in the past videos if you are a regular watcher of my videos, right? If you're a regular audience to my channel, I should say. Okay, so the inputs are very similar to how we actually build a convolution block. You have your input, and you have your filter size, and you have your size, and so on. So nothing more to explain right there. And then there is another function that we will be using as part of our attention, which is it's nothing but a repeat elements function, right? I mean, as part of Keras, you probably know what repeat elements is. If not, if you, I think I put some notes here, right? Yeah, if you have a tensor of shape 256 by 256 by 3, and if you put your repeat to be 2 times, then it repeats this 3 by 2 times, because our axis equals to 3, right? So you'll get a tensor of size 256 by 256 by 6. So it's basically just repeating this 3 times. A easy example that you would relate to is if you have a grayscale image of size 256 by 256, okay? To convert that into a 3-channel image to mimic a RGB, you can just say your repeat equals to 3 times. So you have like 3 of these. That's all this is, okay? And then comes my resconv block. Yeah. So residual convolution block, how am I defining this? You can define this as convolution, batch normalization, activation. Convolution, batch normalization, activation. And then you put shortcut, right? And then batch normalization shortcut. So again, imagine the picture I showed you in the couple of videos ago when we talked about resolutional, convolutional, I'm struggling here to actually say this, residual convolutional layer. Sorry about that. So again, these residual blocks can be different types. Here is one where you have batch normalization and activation. Here is something where you have no activation right here, but then you have activation after you do the addition operation. Okay, after that you have activation. This is what we see in the original image. So let's go ahead and follow this method. Okay. Again, the figure is from this page, and you can go ahead, from this link, and you can go ahead and look at that figure I showed you, showing this convolution, residual convolutional layer. I'm too many residuals and recurrence and things going on, so I'm struggling for words here. Okay, I showed the code a couple of videos ago when we talked about this residual networks. So you have your convolutional layer, batch normalization, activation. Convolution, batch normalization, no activation. Well, if you want, you can add activation, but no activation. You can add dropout if you want. But after this, we are defining a shortcut. A shortcut is basically your X going through 1-by-1 convolution, and then you're adding shortcut and your convolution. That's it. Okay, this is your resconv block. Now comes our attention blocks, okay, or adding attention to your shortcuts. So first of all, let's define a gating signal. Okay, again, if you remember from the image, there is a gating signal, and then you have an actual attention block. So the gating signal is very similar, nothing. It's basically taking your input, and the whole point of this is to resize the layer, the down layer, from your feature map to the same dimension as the up layer, because the down layer has one lower dimensions, right? So it's just bringing it to the same dimensions as the up layer, so you can do some math with it. That's pretty much it. Okay, so all it's doing is a 1x1 convolution, and the output size is the output size right there, and it's acting on your input right here. And then you can perform batch normalization and activation right after that. Okay, so that's the gating signal. And the attention block also, we went through line by line almost in the last tutorial, which is you have your theta x, which is our x operation, and then where is my g? Phi g right there, and x is going through 2x2 strides right there, so the dimension goes down by half. Okay, and your phi is going through 1x1, and where is my add? Right there, you're adding your upsample and theta x. Okay, and then followed by ReLU, remember, and then we perform our psi operation of 1x1, where in my example from last video, you can see that the dimensions goes down to 64 by 64 by 1. These are the actual weights. Right here, you get the actual weights for the attention. But then the weights can go from 0 to any number. So we want to bring them to 0 to 1. That's why we add a activation of sigmoid right there. Okay, and and then the upsampling. So we can go ahead and where is the multiply operation? We can go ahead and perform the multiply operation. So this is all my attention block that I would like to add right after my upsampling. Right after my I believe again, I'm thinking about the graphic, and right at the shortcut connections. Sorry, let me put it that way. Okay, with that knowledge, let's go ahead and put our unit together. Again, instead of using functions, I'm literally using the block, so it makes it easy for us to see. Okay, number of filters, let's start with 64. Okay, 64 number of filters, and each operation we go up by 2 all the way to 16 times, which I believe is 1024, right? And then our filter size is 3, and 3x3 filters, and upsampling is 2, which is very similar to our standard unit. Okay, so the way I'm defining is we have convolution block, max pooling, convolution block, max pooling, right? And what is my convolution block? Again, our convolution block is conv batch normalization activation, conv batch normalization activation, and any dropout if you would like to add. All of that right here. And after that, max pooling. Okay, repeat that, max pooling with 2 times the number of filters, 4 times the number of filters, 8 times, and 16 times. Okay, this is the base right there. And from here, you're doing the up sampling. So then comes upsampling. Obviously, as soon as you do upsampling, you concatenate, and then upsampling, concatenate, and so on. This is our standard unit. And to define an attention unit, this part would be pretty much the same, convolution blocks. You just add a gating and attention block right there before your upsampling. That's it. Okay, same thing here, same thing here, same thing here, and you're done. Now for attention residual U-Net, okay, all you're doing is defining very similar path, except instead of convolution block, I'm using residual convolution block. That's it. Nothing different. Okay, everything is exactly the same. Residual convolution block, the gating and the attention blocks are the same. Everything else is the same. With this knowledge, let's jump into our actual code. Okay, so what are we doing here? Again, importing the libraries, which I already did to save your time. Again, nothing new right there, pretty much the same stuff that you should be familiar with already. And here, again, I'm dealing with the same data that I showed you earlier. I'll leave the link to I thought I showed you earlier, but let's go ahead and look at this. This is the data that we are working with. And these images, you can download these 165 slices, and I cropped them into 256 by 256, both the images and masks, and I dumped them into this folders, images right there, and masks. So I got 1600 of these images and 1600 masks. Okay, now you can do image augmentation and all that stuff if you want. In this case, I'm not using any augmentation, but it should not make much of a difference. Okay, so I get my X test, X train, Y test, Y train. If you want, you can go ahead and look at a couple of images just to make sure everything makes sense. Yeah. Okay. Okay, so everything makes sense right there. They're all matching up, my images and my masks. Fine. Let's go ahead. I don't think I'm using focal loss, am I? Yeah. So I'm also importing. This is something I talked about again a few tutorials ago. But focal loss can be very useful if you want to. Again, this is another way where you're putting more attention in a way towards tough to segment or tough to classify pixels compared to easy to classify pixels, right? So if you already know that you're getting better accuracy on some with high confidence on some pixels, why bother about it? So binary focal loss can be very useful. In fact, I like binary focal loss much better than anything else I'm going to show. Well, I guess that should that's not productive right now, and I don't want to make anyone unhappy, but if you want one quick way of addressing your class imbalance, or one phase or one region is easy to segment compared to the other, go ahead and use binary or focal loss. In this case, I'm doing binary focal loss. If it is multi-class, use multi-class focal loss. Okay, enough of that. Now let's from this file, let's go ahead and import our attention res unit, attention unit, and of course the other coefficient we would like to work with. Once we are done with that, let's go ahead and train a model using unit. Pretty straightforward. So unit model is basically our unit. There you go, my unit, where I give my input shape. In this case, my number of classes is only one, right? One class, and I don't want to add any dropout and batch normalization. I'm putting that as true. Okay, so that's what my unit is, and let's go ahead and compile it. And for that, I'm using Atom Optimizer. And loss, I already mentioned binary focal loss with a gamma equals to 2. Let's not go too aggressive on gamma. You can try 3 or 4 if you if you have a different sample. But for metrics after each epoch or while training, let's track 2 things: accuracy and Jacquard coefficient. And Jacquard is again or it's like IOU, right? Intersection over union. I'll show you the results in a minute. And of course, I'm just doing model.fit. I kept track of the time just to see which one is faster and what type of results are we getting, okay? And I trained for 50 epochs. That's it. And I saved it. I did the same for attention unit. I did the same for attention residual unit. All identical. Binary focal loss and everything is identical except the model is different. That's it. Okay, and I saved the history so I can plot it and all that stuff. But for now, let's go ahead and let's clean this up and see how the models are performing on a few random images. So let's go ahead and define my model as just the unit, not attention unit, not residual, attention residual, just the unit, okay? And let's go ahead and define that. Load the model. And let's import a random image and plot the result right there. Oh, that's very good. You see, I like units. After all of this, I'm like, unit actually does a great job. So, very rarely do you see that, yeah, it can be better, but let's actually keep doing this until we find where it fails a little bit. I don't know. Yeah, let's stop here. So this one, again, it's doing a pretty good job, except it's missing this top one right there. Now, does it do a better job with attention unit? So let's go ahead and load our attention unit right there. Load the model, and let's work on the same image. So let's go ahead and do this part. Okay, so this would be attention right now. Oh, attention, not much, you see. This is regular, this is attention unit. In fact, I like attention unit better, you see. This is regular unit, attention unit, because the shape of my mitochondria is matching this shape very well. This is again regular. You see how this is a bit fatter, and this is attention. Okay, now let's do exactly the same with our attention res unit. So let's go ahead and load that model, attention res unit. And there you go. And let's plot this part of it. And let's see what it does. There you go. So with my attention res unit, now it starts to pick up this part. You see, the top part. So obviously visually you can see that, okay, it's doing a better job up there. And if you go ahead and look at IOU, mean IOU, for example, for this image, it's 90.6 for Attention Res U-Net. So you can actually, here I wrote a few lines of code where it opens each and every image from my testing data, which I think is, how many do I have? 160 images, and then it calculates the mean IOU of all images, because maybe on some images it may be better than the other. So I just calculated the mean IOU of all of these. By the way, if you don't have any features of interest, then when you try to calculate IOU, it may throw some not a number, or your IOU equals to 1.0 because everything is matching. So when I'm calculating mean, I just dropped every image where the IOU equals to 1. That's it. So I summarized all of these in the next set of slides. So let's look at how the summary looks like. Okay, so let's have a quick look, starting with total training images. Just to give you quick information, 1600 images, each 256 by 256. So U-Net finished in 1 hour 6 minutes, 50 epochs, right? And Attention U-Net 1 hour 25 minutes, and Attention Res U-Net, obviously you're adding time, yeah, well, by adding more stuff to do, yeah, while you're training, by adding more parameters. So 1 hour 25 minutes and 1 hour 41 minutes. So adding the res part, okay, the residual part is not adding a lot of overhead when it compares to attention. Attention is where it's adding a somewhat of a additional overhead. Obviously you're training the extra weights, right, for attention part. So, but the point is that really useful? Let's go ahead and see how first the training curves look like. So you're not able to see the other legend there. There should be a legend that tells that, okay, there you go. Let's put all, I don't know why the other stuff is not showing up. So the blue line here is U-Net, and the orange one is Attention U-Net, and the blue one, the gray one is Attention Res U-Net. They completely overlap, almost overlap right there. When you're looking at the loss, when you're looking at the training IOU, they're also overlapping. And if you look at validation, obviously the validation is a bit bumpy because I only have 160 images or so, not much data. So I'm not surprised that this is bumpy. But again, the point I'm trying to make here is I did not see a clear advantage of one over the other. I should also mention I wasn't patient enough. Maybe I should have left another 50 epochs to actually see if one wins over. But up to 50 epochs, I didn't see much of an advantage. But if you look at the final right there trend, I mean, you get Attention Res U-Net slightly higher IOU compared to your U-Nets. But again, this is statistically, to me, they're all very similar. Now let's look at a few random images. I did see a visible change increase in IOU for some of these images. For most of these, U-Net did an amazing job, just like we just saw. You know, one little corner missing, but it's picking up everything else. Yeah. So no visible advantage here, but let's pick a couple of 3 different types of images. Okay. So these are 3 random images that I kind of picked. This is the ground truth. Okay. So this is the original image. That's the ground truth. So with U-Net, it's adding one extra thing right here, which is not present in the ground truth. But I don't blame U-Net. You see here, it looks like something that belongs to this class. So I'm not too much worried about that. It's missing something existing here. So this is a bit of a worry. You see here, this is the true label. And in fact, if you look at the mitochondria, it looks like there is something here. Not sure why U-Net is missing right there. Okay. If I change the threshold, I may actually get some of these, but then I'll pick more of other stuff right there. This is the optimal threshold right there. And if you look at this final image, the IOU is 93.1, and here is the ground truth, and here is what it picked. If you look like right there, you see it's slightly exaggerating the shape of the true mitochondria right there. Okay, so that's U-Net. Now let's look at Attention U-Net. Attention U-Net also picked this small region, and you see how it made this slightly better, but it's still not that ideal, but it's still better than regular U-Net. Okay, and the IOU here is 95.6. You see how this shape is very nicely defined, almost overlapping with these shapes. In fact, it's almost a clear overlap between this image and this image. Okay, so attention really helped in this case. And if you add attention res U-Net, that part is gone right there, only these two. It's almost identical to what we have here. In fact, even this small thing is showing up. You see that small bump right there? I don't even see anything in that image. That's the problem of cropping your images. You don't have the context to get better segmentation, but attention res U-Net seems to have, considering that, but definitely dropping this part that is not supposed to be part of this. Okay, and if you look at this again, this is doing an excellent job, almost identical to your original ground truth label. And your IOU, again, look at this. For this image, the bottom one is 0.96. So attention res U-Net is definitely much better than the ground truth. Well, when I say much better, you see, that much better. So, and in terms of training time, it's slight overhead, but it's probably worth it. Okay. Do I have any other summary right there? Yeah, for all the 260 training or testing images, the average here is 88.8, 89.3, and 90.2 when it comes to IOU. Okay, so overall, there is a improvement in using attention res U-Net, but again, is this really significant enough? It depends on individual use cases. I mean, sometimes you're okay if you get 60% of accuracy, right? In those cases, obviously, it doesn't matter what you use, but sometimes you need to be as close to 9900% as possible. Then in those cases, attention does help. Attention res U-Net does help. Now, there are other variations like R2 U-Net. I tested it. Again, they're a bit slow, but I haven't seen any clear advantage of any of those. In fact, the reason I picked these three is I really liked what I'm seeing with attention res U-Net. So probably I'll pick this if I have a choice. I wouldn't consider R2 U-Net. If you want to experiment with that, in the next video, I'm going to talk about a library that you can use, which makes using any of these models a bit easier. Okay. Again, so please stay tuned for that, and I really hope you learned something useful in this video. And again, go ahead and subscribe to this channel. Let's meet again in the next tutorial.